categories as foundation. Longbeer suggests that that's really more adequate to what we do in a lot of mathematics today, unlike, say, 100 years ago. Mathematics has changed. And I want to bring it up here partly because I think it's a good foundation, but also because it's a good example of a more structured category. We'll talk about what is a generator, what is a push-out. These are things that are important in lots of categories that don't show up as much in the category of sets. Functor categories as adjoint, there was an important discovery that came out of this. And the possibility to categorize categories is, it should be seen as a foundation. One way to look at it is a foundation that's centered on set, but adds a little bit around set. That's just one way to look at it. Talk about what are foundations for. A couple of people have asked me, what are the advantages of categorical foundations? Well, to talk about advantages, you have to know what you want, right? It's an advantage for something. We'll talk about various things foundations give you for. Zermelo's opinion about it. Foundations as truths that organize mathematics, which is Saunders MacLean's view. Do mathematicians outside of logic give proofs? There are philosophers who believe that a real proof is a proof in Zermelo or Frenkel. And so most mathematicians never give those. But mathematicians write instructions that logicians are able to turn into real proofs. So mathematicians don't actually know proofs of their theorems, but logicians can find proofs of them. And this distinction between large, small, and locally small categories, which is one of the things that you might want to know what role they have in proofs. And come finally to philosophical logic. In short, what I want to say, how this influences logic, philosophical logic outside foundations of math. At the very least, it's a much more flexible source of structures than people had before. Philosophical logicians want to find logical systems with different properties, different various properties, and I think philosophers don't realize how easy it has become to design formal systems. We know a lot about it. We can do that easily. Now, that doesn't make it easy to find a good system for the problem. It remains to find a good system. But I think it's time to know that finding systems themselves is pretty easy. And an example, I'll give topos theory and synthetic differential geometry. This is an approach to differential geometry that's really very elementary, used in non-classical logic. And Kripke models as sheaves, Kripke models of modal logic, intuitionistic logic as sheaves. Those are just some things that I wanted to remember to get to. Start with Bill Lavier, the closing sentence of his article on the elementary theory of the category of sets. Oh, that S should be capitalized. So people were asking us, elementary theory of the category of sets. He closed by saying, it is the author's feeling, his own feeling, that when one wishes to go substantially beyond what can be done in the theory presented here, okay, he mentions this theory, for example, it can't prove its own consistency. No theory can prove its own consistency. You might want to do that. It can't prove existence of various large cardinals. You might want more large cardinals than this theory. Also in ZFC, people debate, should we add new axioms guaranteeing certain large cardinals? But it's his feeling that if one wishes to go substantially beyond what can be done here, if you really want to say, if you want to say very much more than what can be done in this theory, a more satisfactory foundation for practical purposes will be provided by a theory of the category of categories. This is really what he's saying. This is how math is being done. At the time he wrote, he wrote this in 1964, so 52 years ago. But it's all the more, I think, all the more true today. Textbooks routinely now go beyond the category of sets. And algebra books, they'll introduce what is a group, and then what is a group homomorphism, that's a U. a group is a set with a certain structure on it. A group homomorphism is a function that relates to that structure in certain ways. And then they will say, they'll talk about the category of groups and homomorphisms. And that's the category that I have called GRP, group, short for group. And they'll start talking about this, and they'll say the category of groups has products. They'll show how to define a product of groups. They'll say the category of groups has co-products, which we haven't talked about, but and they'll show, and they'll talk about the category of groups. Now, the category of groups is too big to be a set. There are actually more groups than there are sets. Well, I mean, in a way, there can't be, if your foundation is ZFC, there can't be more things than sets, because everything is a set. Anyway, for every group, there's lots of group structures. For every set, there's lots of group structures you can put on it. The category of groups is as big as the universe of all sets, so it can't be a set. But they'll talk about it. And they'll talk about functors from the category of topological spaces to the category of groups. I think we talked about this here when I mentioned the one element, the one object category, the category 1, and you take any category A, and it's got lots of stuff in it. And we're not even concerned how much stuff it's got in it. It's got a unique functor to that. Because you just take every object to that one object, you take every arrow to the identity arrow. Of course, compositions are all preserved because it's the identity arrow. Composing it with itself gives itself. And I said, it's really hard to look at this and not think that this is a terminal object in the category of categories of functors. Every category has a unique functor to this one. So you think, okay, it's a terminal object in the category of all categories and functors. Now, but there isn't a category of all categories and functors. Not if categories all have to be sets. You can talk about all the categories because a category is a set, and we can talk about all sets. So you can talk about all categories. But we don't have a set of all sets. So we don't even have a set of all categories, let alone a set that is the category of all categories and functors between them. But you just can't help thinking of it this way, and you shouldn't help thinking of it this way. Now, that's what I here call a non-genuine quantification over large categories. Because a lot of this stuff, well, this thing, we don't have to talk about a category of categories to say every category has a unique functor there. It does. For any category you take, you find a unique functor to that. So we can't quite say this is a terminal object in the category of them all, because there isn't one. But we didn't need to talk about the category of them all to say that each one has a functor there. And this is the sense that Zermelo Frankel talks about classes. Definable classes. In Zermelo Frankel, you can talk about the class of all von Neumann ordinals. Because there's a formula in the language of Zermelo Frankel that characterizes von Neumann ordinals. These are certain rather special sets. They're linear. What they are is they're transitive sets that are linearly ordered by membership. In standard, all the cardinal numbers are von Neumann ordinals. We use von Neumann ordinals. Cardinal numbers are some of these. We can talk about the class of all cardinal numbers. because there's a formula in the language that picks them out. So we talk about definable classes a lot in ZFC, and, well, in any set theory. Maybe to give a more familiar example, suppose we're just going to do arithmetic. We're not going to talk about sets of numbers, we're just going to talk about numbers. We can still talk about all prime numbers, because we know what a prime number is. That's really just a way of talking about numbers. And I'm saying consider any number that can't be divided by anything smaller than it except 1. So I'm not really talking about sets when I say, you know, there are infinitely many prime numbers. Well, let's not quite say infinitely many. The more careful books say, for every number there's a prime number greater than it. The prime numbers are not bounded. There's no bound on the prime numbers. That's not really talking about a set of numbers. That's not talking about a set of all prime numbers. The primes are unbounded. We don't normally say this about prime numbers, but we do about some other kinds of numbers. You could read this as the set of primes is infinite. And people often do say that. But you could also read it as saying, for every number n, there is some prime greater than n. And this clearly didn't talk about sets of numbers. It just talks about numbers. A lot of what you want to say about, say, the von Neumann ordinals or the cardinals, it looks like it's talking about a proper class. But it's really just talking about individual sets. Not everything. Sometimes Zermelo-Frankel set theorists want to talk about the class of all sets. And then they have a foundational problem because ZFC itself won't do that. But not most of the time. Most of what they say that looks like, when you read a book like, I think this is Kunin has a nice passage I read. That's anyway, standard advanced books on set theory talk about proper classes and normally say, we'll talk about proper classes, but we always mean definable classes. That is, all x such that capital phi of x, where capital phi is some formula in the language of set theory. So really talk about proper classes is talk about formulas, is talk about definitions in those books. Like I say, there are some ways of talking about proper classes that have to go past this. Notably, if you want to quantify over classes, if you want to say every class of sets that has this property has that one, or more especially if you want to say for every class of sets there exists a class of sets that has such and so property. Now maybe you don't have definable formulas anymore. So there are things that go beyond that, and sometimes set theorists do. But a lot of talk about classes doesn't go beyond set theory, and neither does a lot of quantification over large categories, but some does. Some absolutely does. What you will find not in a first or second year graduate textbook, but in some more advanced graduate texts on topology, we really want to quantify over. We want to say there exists a function from topological spaces to groups such that something or other, or maybe you I mean, sometimes you really do, you want to consider infinite collections of functors from topological spaces to groups. And at that point, you really are, you do need these things to be things, actual entities. You can't do that in Zermelo-Frankel as it stands. Well, we'll come back later to some ways to handle that problem. But Laubier's idea of how to handle it was the category of categories, which I want to introduce to you anyway, because it has these interesting properties. To describe a particular, we described the category of sets. The category of sets doesn't have a lot of structure. Sets don't have a lot of structure. A set is just a collection of things. That's all there is. How many things is all the structure a set has. Categories have a lot more structure than how many things. Here's a two-object category, a two-object category that has two arrows. It's got two objects, they each have their identity arrow. I don't draw the identity arrows. And that's all. It's got two objects and identity arrows. So we often call this thing 1 plus 1. Because it's just I just combined two copies of one. Now here's a category with two objects, 4 arrows, because there's the two identity arrows that I didn't draw. Here's a different category. No, that's like too much. Here's a different category with 2 objects and 4 arrows. And in fact, I haven't told you what category this is, because if we call this thing F and this thing G, we've got to know what is G composed with G. We got a choice here. It's got to be an arrow. It's got to be an arrow that starts where G does and ends where G does. But there's 2 of those. There's one category. Let's call this alpha and this object beta, where that's once a beta, G is its own inverse. That gives a category. There's a different category. Well, I'll draw them as alpha and beta now. I'll call this one H. HH equals H. Those are two. These two are different categories. They have the same number of objects, same number of arrows. They even have the same, if you just draw where the arrows are in the same places. But they have different composition laws. So there's just a lot more going on in a category than there is in a set. Oh, also here, I also have to know what is G, F, do F and then G. And let me see, what choices do I have there? F and then G, right, no. That has to be F. It has to be an arrow that starts where F does and ends where G does. And there is only one arrow that does that here. So that's good, it's going to have to be that. Here I have to know what is H then F, but also there's here I have no choice either. That also has to be F. You know. But I do have a choice about this thing. Is this its own inverse, or is this what we call idempotent? Once you've done it, you can do it any number of times, and it doesn't change the thing. So categories, if we're going to describe a category that has stuff like this as its objects, we're going to have to say more about things than we did in the category of sets. The category of sets, the crucial feature was that a one-element set is what we call a generator. A generator means you've got a pair of objects and a pair of arrows between them. How easy is it to tell whether these arrows are the same or not? I've drawn them as separate, but maybe they're equal. Well, in the category of sets, remember we said, if f is not equal to g, then there exists some x, well, I'll call this a, from 1 to a, such that fx is not equal to gx. Now what I want you to think of what that means is the terminal object in set suffices to test equalities of functions. And it's called this testing equality. Whenever things are different, there's some element here making the composites different, then functions from 1 to a are enough to test equality. Now, in the category of categories, we have the one-element category, and let's look at the category E, which is the one. I guess I better label these things: alpha, beta, F, G. We had the functor from here to there that picks out alpha. You know there's a functor from here to there that picks out beta. But those are not enough to test equality, because E has two functors to itself. There's the identity functor. I don't have room to draw this very... The identity functor will just take everything to itself. You can see there's another functor that simply switches F and G. It takes F to G and G to F. It still takes alpha to alpha, beta to beta, but it switches those two arrows. I hope it's clear to you. That looks like it should be a functor. It is. There's really no compositions to be preserved here except compositions with identities. But composing, let's take the functor, I'll call this functor alpha because it picks out object alpha. Composing alpha with those two functors from here to there still just gets alpha, right? Because those functors took this object to that object. And composing those two functors with beta just gives beta, because this took beta to beta. Functors from 1 can't tell the difference between those two functors. 1 cannot test identity of functors, because functors from 1 can't tell what happened to the arrows. Two different functors here can do the same thing with the objects, but different things with arrows. And I'll tell you one sort of guide to thinking about categories. Anything that happens in really simple examples like this, it happens in serious examples too. I mean, I don't want to give serious examples of categories that have multiple functors that do the same thing on objects. But believe me, it happens with serious categories too. You know, this is not enough to test the equivalence of equality of functors. But the category 2, well, okay, I'll call them 0 and 1 here. The category 2 that just had one arrow in it, this is enough to tell those apart. This has a functor here that picks out F. And I'm going to call that functor F. because it picked out the one I've labeled as f here. Now if I do f and then the identity, I still get f. But if I do f and then the functor that switched the arrows, I get g. So this is enough to test the difference between those two functors. And in fact, this is enough to test the difference between any two functors. We have arrow extensionality. For any two functors between the same categories, of course, if they don't go between the same categories, we don't have to ask whether they're equal. They're not. The only way they could be equal is if they go between the same categories. But for any two functors between the same categories, if they're different, then there is some functor from 2 to the domain where the values are different. And I'm afraid maybe after just these 2 lectures, not much about category theory is obvious to you. But I hope you see it's obvious that whenever I've got 2 categories, I've got some category here and some category here, and this is some network of arrows, and this is some other network of arrows. A functor takes arrows from here to arrows there. And once you know what it does to the arrows, you know what it does to all the objects. Because every object has an identity arrow. And once you know that the object has to go wherever its identity arrow went over here. So 2 functors, they might do, I have 2 different functors to do the same things on objects. But if they do the same things on arrows, they're the same functor. In other words, if they're not the same functor, then there's some arrow that they don't do the same thing with. So this looks just like extensionality in the category of sets, except that there we said there's some arrow with domain 1 that distinguishes them. Here we're saying there's some arrow with this domain 2 that distinguishes them. Now 1, in the elementary theory of category of sets, we knew what that domain 1 was. It's a terminal object. If we're going to axiomatize the category of sets, how are we going to pick out this object? Our axioms have to tell us which this object is. Because I've been telling you by drawing pictures on the board, but our axioms cannot look at pictures. We could say, oh, the set of objects has 2 things in it, and the set of arrows has 3 things in it, if we are giving set-theoretic foundations, but we're not. That's the purpose now, is to axiomatize the category of categories directly. So we need to be able to describe this category 2 directly in terms of functors. So we define in the category of categories as foundations. First, 1 is a terminal category. We need this category 1. We say it's a terminal category. Every category has exactly 1 functor to it. Same as we define the terminal set, every set had 1 function to it. Every A has exactly 1 functor to it. Two, well, now 2 has 3 functors to itself. It has a functor that I'll call 1 sub 0. A functor, it has the identity functor itself. It has to. Everything in every category has an identity arrow. and has a functor I'll call 1 sub 1. And 1 sub 0 is a constant functor. It factors through the identity, through the terminal object, the one object category. So now we define in CCAF an object of A is any functor from 1 to A. Just like we said, an element of a set was any function from the singleton set to that set. We now say an object is a functor from the terminal category to A, and an arrow of A is any functor from 2 to A. Because now we're giving axioms where our primitives are category and functor. We know that every category has an identity functor. We express the Eilenberg-MacLean category axioms. We say every category has an identity functor. Every functor goes from one category to another. When one functor goes from one category to another, and the next functor goes from that category to a third, there's a composite functor. Composition is associative. An identity functor is composed by not changing the thing. What the Eilenberg-MacLean category axiom said for objects and arrows in every category, we now say for categories and functors. But we're not defining categories and functors as having sets of objects or sets of arrows. We're not defining them starting from set theory. We could do that, and Eilenberg and MacLean did do that. But we're doing a different project now. We're axiomatizing the category and categories directly. So all we know in the first place about categories and functors is that the functors compose and they have identities. Then I say, well, okay, there is a terminal category, and there's a category with 3 functors to itself, like this. 2 of them constant functors, and then the identity, because the identity had to be there in any case. So now, we have to ask about composition. Well, I'll do it on the board here, yeah. What's the composite of this functor with that? Notice that this functor ends at where that one begins. What's the composite of these 2 functors? This is an identity functor, so it has to be that one. The composite of these 2 functors, this is an identity, it has to be that one. The only thing that's a little tricky is, let's take I sub 0 and compose it with I sub 1. What's the composite of, I don't know, maybe it's worth looking at it this way. Blank this out. What's the composite of this functor with this one? It's easy to tell because, well, I'll draw it on the board here. The composite of this functor with that one, remember, this one factors through 1. And this one factors through 1. So the composite of those 2 has to be the composite of those. And anything to the terminal object this is unique. The functor from 2 to 1 is unique. We don't have to ask what this composite is. It is the only thing it could be. So the composite is that second one. These are what are constant functors. An arrow in any category let me draw it a little bit more. In any category, we call a functor, an arrow, we'll call it constant if it factors through a terminal object. What what do I mean by constant? Intuitively, if you think about sets or categories now, this thing had to mash everything down to that one point. And then it just inserted that as a single point of B. So if my original arrow factored this way, it had to mash everything in A down onto a single point of B. So there are two functors. Two of them are constant functors in the precise sense that they factor through terminal object. And that tells me what all the composites are. In a more complex situation, I might have to talk more about composites, and in a moment I will. But for this, I don't need to say anything more about how those functors compose, because one of them is an identity, there's nothing to say about how it composes, and two of them are constants. And in any category, if I map A to B by anything, and B to C by anything, and C to D by a constant arrow, all of this is deleted. The composite has to be that, because it went through the terminal, and the terminal is, there's only one arrow from A to the terminal object. So I don't need to tell you how those compose. So as soon as I've told you, so an arrow is that. And now I can say, I'll call this arrow F. The domain of F, I'll call this the arrow domain. Because the point is, if I'm looking at this as a functor, the domain is 2. This is a functor from 2. But now I'm looking at it as an arrow in A. I said an arrow is a functor from 2. So looking at it as an arrow, what's the domain of this as an arrow? Well, is it's this composite. Let's draw that. The category 1 looked like that. The category 2 looks like that. The category A, we don't know what it looks like. It's some network of arrows, but the functor picks out a certain one of them. We want to pick out the domain of that functor. That's what this went to. So take the functor from here, 1, that picks that out, and compose. That will give me, if I'm thinking of this as an arrow in A, composing with this functor would give me the domain of that arrow. So it's this composite, and that makes sense. The domain of an arrow should be an object. Objects are functors from 1. This is a functor from 1. The codomain I define is, well, it's of course what you would think. Let's not pick out 0, let's pick out 1 and compose. And then the composite will pick out that object. So, not all philosophers who talk about category theory have understood this. I'm not defining a category as a set of objects and a set of arrows. I'm simply defining a category as a point in a network of functors. And then I'm defining what objects are as functors. I'm defining what arrows are as functors. I'm defining how to get the codomain of an arrow, compose it with this, how to get the domain, how to get the codomain. So now I've defined what is an object of a category, what is an arrow of a category. I have not defined composition of arrows in categories. And this is the point that I want to make clear. When I'm defining this special category, I'm going to have to talk about some special things in it. What is it that makes the category of categories different from the category of sets or the category of groups? Well, one thing that makes it different from the category of sets is that the singleton, this thing, is not a generator. We don't have extensionality for these. It's a little bit like sets because we do have extensionality for functors from this thing, and this thing has exactly 3 functors to itself. So now we know this has 2 objects, well, 2 identity arrows. Yeah, if we want to be really picky about it, we can say what is an identity arrow? Well, arrows are functors from 2. An identity arrow of A is an arrow, well, and it better be an arrow, but it is the identity functors, our identity arrows are the constant arrows, the ones that factor through 1. So now so as soon as I told you this category has 2 objects, 2 identity arrows, 1 non-identity arrow. And in fact, I've told you that the domain of the non-identity arrow is different from the codomain. So intuitively, it's got 2 objects, it's got 1 non-identity arrow. You might think that's here, or maybe it's here, but no, I've said the domain and codomain are different. There's only one way to put an arrow here, and the domain and codomain different. Well, of course, you could go the other direction, but that doesn't matter because we don't know what these are. So this somehow defines 2 up isomorphism. But we haven't given enough axioms to make that definite yet. If I was defining a category of modules over some ring, then I would have to tell you special stuff about them, relating them to that ring. If I was defining a category of differentiable manifolds, I have to tell you some special stuff about some of them. If I'm defining a category of groups, I have to tell you some special things of sets. Here I'm defining a category of categories, so I have to tell you some special things about categories. And I need to talk not only about the 2 I have, I need to tell you about the category 3. Category 3 is a push-out. I haven't defined what is push-out. What that means is category 3 has at least 2 arrows. I'm telling you there are 2 arrows, alpha and beta. It has at least those. And then I'm telling you something special about those 2. Alpha composed with 1 is the same as beta composed with 0. But remember, what is alpha composed with 1? That's the codomain of this functor. If we regard this as a functor in the category 3, an arrow rather in category 3, yeah. If this functor is an arrow in 3, I'm saying the codomain of the arrow in 3 is the domain of this other arrow. So 3 looks, so far, I've told you the category 3 looks like it has 2 arrows, and the codomain of one is the domain of the other. And in fact, the codomain of alpha is the domain of beta. I've told you the category looks like this. And furthermore, this push-out property means for any category A, if it has arrows F and G, if F1 equals G0, that is, if this composite equals that one, then there is a unique U. Remember, well, our definition of a terminal object in any category was take any object, it's got a unique map. Our definition of product was a little more involved. We said take any object, if it's got arrows there and there, then there's a unique one here. Now we're saying take any object, if it's got an arrow from here and an arrow from there, and they make these composites equal, then there exists a unique U as shown, a unique U from 3 to A, such that U alpha is F and U beta is G. What's the property of this U? It is that if you go like this, you get that thing. And if you go like this, you get that thing. Same as over here, the property was, if you go like this, you get that one. If you go like that, you get that one. So we call it a push out because it pushes an arrow out. Anytime you have some way of getting out of here that makes those equal, you can push it through here. Here we had anytime you have some way of going to both of those, we didn't require any inequalities here. As soon as you have a way of going to both of those, you can push it through there. But here we pushed it to the product. We're pushing it out of the push out. And there is a functor gamma there is one other category, there's one other functor, one arrow within it, where gamma 0 is alpha 0. So this thing gamma, it starts where alpha started, and it ends where beta ended. There is an arrow like that. So now I've told you there's two arrows. There's two arrows in here that compose, and there's a third arrow. Well, I haven't defined composition yet. But there's two arrows here where the domain of that is the codomain of that. And then there's another arrow whose domain is shared with that, codomain with that. I haven't told you there are no other arrows. But maybe you'll believe me when I say this push-out condition. This tends to mean that there can't be other arrows because this functor has to always be defined. And if I put other arrows, and it has to always be unique. If I put other arrows, I might get more choices about what to do. But my defining condition was I don't have any choice about what to do. Now I can define for any f from 2 to a, so any arrow in a, and g from 2 to a, so now any two arrows in a F1 equals G0. What does that mean? That means take the codomain of this thing as an arrow in A, right? We compose with one to get the codomain. If finding the codomain of this is the same as finding the domain of that, the composite in A, right? I mean, as functors, these don't compose because they both go from the same. But as arrows of A, it's a little confusing to talk about category of categories. The composite as arrows of A. Well, what should that composite be? Let's look at it. Let's take a picture of A. My picture is I've got this arrow F and I've got this arrow G, and they match up like this. F and G match up like this. Which is the defining property for the pushout. So there's a unique U. So now there is, from my category 3, which looks like this, there is a unique functor that takes this one to F and that one to G. That's the pushout property. Is U gamma, which goes from 2 to 3 to A. Right, I mentioned there is another gamma that goes from 2 to 3. This is a functor. Compose it with that. That gives me something there. So what I've done is, the pushout property said, given any two composable arrows, there's a unique functor from here that takes them to that. Now I've defined the composite as being as per this wind. This had to go to some arrow there. So now I'm defining the composite as that pushout. Now, so far I haven't told you that there aren't other arrows in here in 3. I haven't really told you that 3 looks like this. I've told you 3 has at least these arrows. But by combining the pushout property and the other axioms, we will in fact prove that it does have no others. So now I've defined object, arrow, identity arrow, composition. And now it's a theorem. It follows from the axioms for each of the Eilenberg-MacLane axioms. Remember, the Eilenberg-MacLane axioms said every arrow has a domain and a codomain. Every object has an identity arrow that goes from it to itself. Any two arrows that match up correctly have a composite. Composing with identities doesn't change what you composed with, and composition is associative. For each axiom. And what should we call an axiom? I'll call it capital Phi. Yeah, for each axiom capital Phi of the Eilenberg-MacLane axioms, we can now interpret that in CCAF. We know how to talk about an object of a category, an arrow, an identity arrow, and a composition. The CCAF axioms will imply that thing. These definitions verify all the Eilenberg-MacLane axioms. I mean, for example, one axiom says every arrow that's a functor like this has a domain. Well, indeed it does. It's that composite. It said, the axiom said, every object We now interpret an object as a functor from 1. Every object has an identity arrow. Yes. That one. So we've now given an interpretation of what is an arrow, what's an identity arrow, and this interpretation makes all those axioms true. We did not define a category as a set of objects and arrows. We axiomatized categories by saying some special things about categories. When you think about it, obviously you're not going to be able to axiomatize categories without saying some special things about them. But we were able to do it without talking about sets of objects, sets of arrows. We were just putting axioms on categories and functors, and we can verify this. So now, in that sense, each of these things is a category. Each of these things, we know what we mean by an arrow in it, we know what we mean by an object, and the objects and arrows do satisfy the category axioms. So these things are all categories. Now, if we just define, here we're taking functor as a primitive, how do I know that every functor here takes objects of A to objects of B? Well, what is an object of A? An object of A is a functor from 1. And indeed it takes that to an object of B. Just compose. How do I know it takes every arrow of A to an arrow of B? Well, the same way. An arrow of A is a functor from 2. Call it F. So you compose. Does this preserve domains? Well, what's the domain of this arrow? The domain of this arrow is that composite. And yes, it doesn't matter whether I compose with this. So, do I compose these two and then compose with that? That's the domain of the value. Or do I compose these two and then compose with that? That's the value of the domain. But the associative axiom in the first place said that it doesn't matter what order I do it in. So sure, composing this thing is now the functor applied to the domain, or the domain of the functor applied to the arrow. Either one. It's both, because associativity holds out here. So the objects are now, they are categories. I know what is an object, what is an arrow. I know how to compose arrows. The functors are functors. They automatically take objects to objects, arrows to arrows, preserve domain and codomain, and preserve identities. So these axioms then let me prove things about the category of categories. Okay, so now is a good time to break. Now might be a good time if any of you have questions, come up and ask me, because I'm not, this is new stuff. So, and I want to explain it sufficiently. So let me know if I can explain any of it more to you. Okay, we're 10-minute break.